the visitors and also the volunteers of all ages in the booths. It shouldn't be too expensive, and since network coverage on the festival cannot be guaranteed at all times, it must also be able to work offline. Also, it would be beneficial for the customers to check their balance on the cards by themselves. So this is the hardware version 1 that we came up with back in 2019. It's made of many off-the-shelf modules soldered onto a custom carrier board. It's based on the ESP8266 microcontroller. It has a module, it has a text LCD screen. It used back then micro SD cards for the storage of the transaction data, because this is one of the benefits you have with such a system. You can afterwards analyze the data on the purchases over time and at what locations things were sold. It uses a 4x4 membrane key matrix, and back then we used laser cut acrylic cases we glued together. Due to the small bill of materials, the cost was acceptably low at $15 a piece only. You can see the system in action. We also had our own cards printed and made. The system worked well for a couple of years, but nevertheless there were a few shortcomings. So back in the fall of 2023, we decided we want to make a new version to tackle these shortcomings. So this is what we decided to change. First of all, the keypad matrix was read out by the microcontroller using only a single ADC pin and a resistive divider. And it turns out if you press one of these buttons often enough, its internal resistance changes, messing up the readout. So this needs to be changed. Also, there was a buzzer hardwired on the board to one of the pins of the microcontroller that happens to be high during the programming of the chip, making it quite uncomfortable doing software development for it. Also, it needed, it was relying on external USB power supply, so either having a power bank or a wall adapter in all of the booths. There was no internal date and time keeping. So you had to enter date and time each time you booted the device up, and as you can imagine, not everybody did this all the time, messing up some of the data. There were issues with the screen, but even bigger issues with the storage of the purchased transaction data on a FAT file system on the SD card, so we lost quite a few of those during the way. And also the reliability of the case came to its end. So this is what we came up with for last year's festival's implementation. We made new devices, 50 of them, for improved reliability, usability, and style. You can see the main board here on the screen. More of the hardware moved to the main board, less of the external modules. This time it uses an ESP32 microcontroller with additional flash inside the module, so no longer relying on the SD cards. It also has an internal battery with its own battery management based on a DC-DC converter for efficient and fast charge of the quite large battery. It also uses a DC-DC converter for supplying the 3.3 volts to the devices and the modules, making efficient use of the battery charge, so the battery lasts for more than a day of use. So there wasn't the issue to have it running low during the day. We again used an NFC module, a different one this time, and the device also has an internal real-time clock now keeping track of date and time. We reused the same matrix keypad, but this time read it out with a scanning GPIO matrix to avoid the problem of the resistance of the buttons getting worn out. We changed to a graphical OLED screen for better readability and also better user interaction. And also decided to go with an off-the-shelf case and made the electronics in such a way that it fits nicely into the case. The cost was increased to a still acceptable level of around $60 per device. So the date of the festival was approaching last year, and we had working prototypes, so we decided to have the full batch of 50 boards manufactured in China. And once they finally arrived, after some trouble with DHL and the customs, none of them could read any of the cards. So it soon turned out that the NFC module, the red thing on the screen, was the culprit. But we had working ones and we had not working ones. So I started switching components from one of the boards to the other to see when the fault moves. And it turns out that there are two capacitors on the module that are made for the antenna matching circuit. And it turns out that even you can buy those modules all over the place on AliExpress and Amazon, everywhere. They look all the same, but they are not populated with the same items. So there are capacitors that have a well-tuned antenna matching circuit and not so well-tuned antenna matching circuit. And it turns out the one that we received were not so well-tuned, and the positioning of the module on the board is not optimal. So there's an internal ground plane on the green main board that interferes with the antenna. And with the well-tuned circuit, it reads the cards good enough to read them reliably at a close distance, and with the one we received, it did not. So the problem was solved by just exchanging those two capacitors on all of the 50 boards, and after that, they worked flawlessly. So those are the two capacitors in question, and with these impressions from our assembly session few days before the festival started, getting everything ready just in time, I hand over to Daniel.
So I'll now talk about the system itself and the software side of it, and also how our cards actually work. So when talking about those systems, I want to make a distinction between two types of system. One is a centralized system, and what we have, I would consider a decentralized system. So for centralized systems, this is what you see with like most public transport networks nowadays, is the card basically only is an ID, and your reader is connected to a backend. The balance on the card is stored on the backend. That's a really nice system. It makes it easy in terms of security. You don't have to write to the card because the card basically always only presents the ID. So that's the system that most of those RFID NFC systems go for. But we didn't go for it. We went with a decentralized system where the actual balance of your card is stored on the card itself. So there is no network required, which was one of our requirements in the first place. That's why we went with this system. But it poses a bunch of questions in terms of security. You also have to write on those cards for every single transactions, which poses a bunch of challenges, and I want to talk about those. So first of all, let me give you some more context about those cards. So we're using MyFair Ultralight EV1 cards. They cost us about 16 cents, including the printing on both sides from China. We bought about 6,000 of those cards. They have a 7-byte ID that is unique to each card and that is burned into the card, so this ID can't be changed. And then there's a payload memory of 48 bytes, which we're using to store the balance and the number of deposits you have on your card. There are a few other features, a monotonic counter, which I talk about in a minute, and those cards, which is really important for us, are NDEF compatible. NDEF is the standard that you might be familiar with that allows your phone to read NFC tags without having any specific app. So NDEF defines a bunch of well-defined data types like URLs, and then you can just tap your phone on an NDEF compatible NFC chip and it reads it. And that's precisely what we are using that allows our customers to read the balance from their card. So if you have one of those cards and you just tap your NFC-enabled phone on the card, it opens a web page, and the web page shows you the balance and the deposits that are stored on the card. And it also might show you, as you can see here, the transaction history of your card. So as I said in the first place, we are a decentralized system. So our terminals at the time when we're selling something might not have any connection. And if that happens, the terminal can't upload the transaction details. And if you're a German speaker, you can see the second row where it says like details are still missing for this transaction. So we know a transaction happened, but the details of the transaction haven't been uploaded yet. That's how it's shown to the customer. And as soon as the device then comes back online, those details are filled in. And this makes it really easy for our customers to check the balance on their card. But how does it work in detail? And how can we see the up-to-date balance on the card, even if the device might be offline? And here we're using the NDEF standard to basically what we're storing on the card is just a URL. The URL contains this base64 encoded string. And this string is just a bunch of data. And this, here you can see we have 2 bytes that store the balance of our card. That also tells you how much money you can top up on the card at a maximum. There is another 2 bytes where we store the deposits. We have this counter, which I'll tap on in a minute, that is incremented for each transaction. And then there's the card ID and the signature. And all of that is encoded in this base64 string that is part of the URL, right? So when you tap your phone on the card, all the information about the balance of the card is transferred to your phone basically as part of the URL, and that allows us to show you always the up-to-date balance of your card, even if our device at the time of purchase was offline and hasn't uploaded its data yet. When you talk about a system like this to a crowd like this, the first question you always get is about security of the system. And I'll talk about this now, but before I got into this, I want to preface with saying security is not our biggest concern. We are a volunteer-run community festival. If you really want to steal from our festival, there are a lot easier ways than hacking NFC. Probably you can just convince one of our barkeepers to give you a beer for free. So that being said, we thought a lot about security, and I want to discuss a few of the potential attacks against the system. And with every list of potential attacks, this is never an exhaustive list. I'm sure there are millions more. There are some I included there. There are more that I thought about, but I didn't include. And I'm sure there are also many that I didn't think about, and you guys can tell me afterwards. So the very first possible attack that you can think of is you just modify the balance on your card, and now you're rich, right? There are 2 mechanisms that prevent this. The one is those cards have a write protection with a password that's part of like the MyFair standard. Each card has a unique password that is derived from the card ID. So even if you're able to write one card, this doesn't allow you to write on all the cards. And then you've seen in the payload of our data, there is a signature that's basically computed on every write on the card. We update the signature, which includes your current balance. So that prevents you from modifying the balance on your card. The next thing most people think about is what you usually would refer as a replay attack, right? So you top up your card, you read the value, then you buy a bunch of beers, and then you write back the old value on your card, and you are still where you were before you spend your money. So this attack requires you to have write access to the card, which you usually wouldn't. But let's say you have write access to the card, and then this is prevented by this monotonic counter. That's another feature that's part of those MyFair cards. So that's like just a counter on the card that's incremented with every write. And we include this counter, as you've seen, in our signature, right? So let's say you top up your card, you read the value, then you buy a bunch of beers. When you buy the beers, we're incrementing the counter by 1. If you're then rewriting back your old payload, the counter values do not match anymore, and so that's how we're preventing a replay attack of values. Another idea for a potential attack is you just create your own cards that behave however you want, right? That's how you can get around the write password protection. Maybe you have a manufacturer that generates cards that have a counter that can be modified. And a way how we protect against this attack is by a password challenge. So basically how this works is the terminal, when you tap your card on the terminal, sends a challenge to the card, and the card responds with a response to this challenge, which can be verified on our terminal. And how this response to the challenge is computed is basically programmed on the card. So if you have your own card, this card wouldn't know how to respond to the challenge. So that's how we can protect against fake cards. But also, honestly, I think you would need to get into printing your own cards, and so that's already a quite advanced attack. So another more realistic scenario of attacking our system would be just stealing one of our terminals, right? So we have those terminals, and they can do both. They can deduct money from your card, but they can also top up your card and add more money to your card. So what if you just steal terminals and then you like top up your card every single time? That would work. And what we try to do to preventing this is those devices, by default, if you turn them on, they can only deduct money and cannot top up cards. And then we have a separate NFC token that you have to put on the devices. It's a token like this. You like hold it on the device, and then only it gets into this top-up mode where you can top up cards. As soon as the device is disconnected from power, it goes back to the charge-only mode. So if you steal a device, you continuously need to keep it plugged into a plugged-in power source. So this doesn't work with battery power. So again, doable, but would be a quite advanced attack to like steal a terminal. I'm sure there are more attacks. So for example, probably if you get your hands on one of those devices, and like you can probably get out our private key of the chip on the device and so on and so forth. But again, like maybe it's easier to just ask the barkeeper for a free beer if you're really that desperate. Another topic that I want to talk about, as Andre mentioned, we started out with SD cards on our first generation of the devices. So every time a transaction happens, we write a transaction log. And that's really helpful for us, not in real time, because those logs might not be uploaded. But at the end of the festival, we want to be able to see how much we've sold, right? So in our first version, we used those micro SD cards and just had a single log file that for every transaction we appended a line to this log file. That was the first year in 2019, I think, and we do not have a single log from that year, because eventually when you're writing thousands and thousands of lines to a file, something goes wrong. Eventually your file becomes corrupted. The next time you're trying to write to a corrupted file, you're writing to an arbitrary position in the file, and all your data is lost. So that was year one when we were using this system. We moved on, same hardware, so we still were using micro SD cards, but we just wrote an individual file for each transaction. We generate a client-side unique ID for each transaction, and then even if one transaction file is corrupt, we still have the rest of the transaction. That worked better, but we still had a bunch of problems specifically to the reliability of micro SD cards, and I think I blame a lot on the FAT32 file system as well, which is really not meant for a system that can lose power at any time, and these kind of things. So with the new iteration of the hardware, we went to an internal SPI flash, which so far has been super reliable, and we did not lose a single log file in last year's festival. We also moved to a different file system called LittleFS, which has been super reliable for us, and this file system is specifically designed for use cases like this, where, for example, your device can lose power at any time, can reboot at any time, and these kind of things. We also started, instead of just having plain text file, to use protobuf encoded files. If you're not familiar with protobuf, that's a binary encoding for where you can define your data structure. First of all, it's more efficient, but also it gives you type safety, which is really nice. So what you can roughly see here on the right side of the screen is how one of our log files looks like. So it contains all the transaction data. It also contains a bunch of health data about the device, for example, battery voltage, USB voltage, and these kind of things. That just gives us some insights in, like, okay, is this device still alive? Is it working as we expected? And so this last year was the first year we used this system, and we haven't lost a single log file last year, so that was a really big improvement. And what it gives us at the end of the festival are statistics like this, right? So here you can see the 3 days of our festival, and you can see a day usually starts slow and then ramps up over the day. There's like the peak time at like, it's about like 8 o'clock or so where our peak time is, and then it tapers off on the end. You can see Sunday people are exhausted a little, so Sunday is a slower day for us. But yeah, that has been super insightful for us as a festival. And as I said, those statistics might not be available in real time to us, but have been super helpful for us. So I want to wrap it up with how we're thinking about the system going forward. So as I said, last year was the first year where we really had no problems with the system at all, and we were super happy. We didn't lose a single device during the festival. We have all our logs. So now we're thinking about, okay, what is there that we can do more? So what we're currently working on is the crew at our festival eats and drinks for free. So everyone who volunteers gets food and drinks for free. We still want to keep track of this just to know how much free food we're giving out. So we're introducing a wristband that has an NFC chip on it. So whenever someone from our crew picks up some food, they can scan the wristband NFC chip, and then we just write a log. We don't like charge any money, but we still keep track of what's happening. Another really interesting discussion, we are currently in talks with Apple trying add this system to Apple Wallet. Apple really has no interest in this whatsoever, but then there are some EU regulation that prevents them from locking out people of doing this. So we had some funny meetings with Apple. I'll not go into this because of time, but like, find me later and I can talk to you a little about this. I'm not super hopeful that this will turn out, but I keep annoying Apple with this because it's just fun. And then there are a bunch of more extensions that we can do. We're using the ESP32, which has a Bluetooth chip on it, which we're currently not using. So we're thinking, for example, employing Bluetooth-based receipt printers. We could, currently the top-up happens at a point of sale where a person tops up the card. We could add vending machines where you could top up your card. I'm also really interested in mesh networking, so even if you don't have reliable internet connection, we could send the transaction data from one device to the next device to the next device until maybe one device has a reliable network connection. So I think this gives us a lot of opportunity for the next decade to work on, and yeah, that's our system. So thank you so much for listening to us. Oh yeah, and we do have the different hardware variants and iterations with us, so if you're interested in having a look at them or even seeing the system working, find us somewhere around here and we're happy to show it to you. Thank you.